All right. So thank you for the invitation. I would like to speak about my recent work with my PhD students, Gonzalo and Rifat, about Cauchy slice holography. So in the usual ADS CFT holographic duality, the dual CFT lives at the spatial infinity of anti-de Sitter spacetime. But recently, there's been a lot of interest in the so-called TT bar deformation, or it's called T squared if you're in D greater than 2 boundary deformation, D greater than 2 boundary dimensions. So this is an irrelevant deformation that has, in the field theory sense, that has some nice properties I'm going to write down later. But what it does is it's dual to a bulk anti-de Sitter spacetime that has Dirichlet boundary conditions. But the way we're going to interpret this is a bit different from how it's usually done. So usually the way people think about it is if this is the tin can model, where the CFT is out here at the boundary at spatial infinity, then the way people usually think about it is the T squared deformation pushes in the boundary to a smaller cylinder that's at finite radius, so it acts as a sort of IR cutoff on spatial infinity. What we did is we wanted to play a variant of this game where we did something else, where instead we had our holographic T squared deformed field theory live on a spatial Cauchy slice of the anti-de Sitter space-time, which is more inspired by the sorts of things people do in tensor network models of quantum gravity, but sort of like a continuous tensor network. Now, it turns out you can actually do this with the same irrelevant T-squared deformation that you would do to implement the picture on the left. You just start with a different geometry. So I'll show how that works. But first, here's the names of my PhD students that are likely to be on the market this fall, Gonzalo and Rifat. All right, so what we're looking for here is a field theory that lives in D dimensions whose partition function is also a Wheeler-DeWitt quantum gravity state. So what that means, we have an equation that's like Z equals psi, where Z is a partition function of a Euclidean signature. You should think of it as if it's a QFT on a fixed background metric, except you're allowed, as usual in field theory, to vary that metric to get different answers for the partition functions. So it's going to be a D Euclidean, and this is a little bit of a misnomer, but I mean Euclidean space-time dimensions in the sense that we have a partition function on this left side and not a state. So it depends on the background metric, and it depends on some other set of sources that I've written out like this. Okay, so on the right-hand side, we interpret the same number, the same function, to mean something else. We now interpret the metric G as the spatial metric of a theory in D+1 space-time dimensions. So we think of it as the Wheeler-DeWitt metric of space. So these are configuration variables. And the matter in the theory, the sources on the left-hand side will now look like matter fields. It could be scalars or fields with spin of various sorts on the right-hand side of this dictionary. So the most obvious thing to do with a partition function is to differentiate it with respect to the metric and get a stress tensor. So this derivative with respect to the metric, on the left-hand side, we would call it the stress tensor, but it has a different interpretation on the right-hand side. On the right-hand side, it's what we would call the ADM momentum. That is just like a quantum mechanics conjugate momentum operator for the spatial metric. Now, there's some factors here that are really not very important. It's just a matter of convention about whether you densitize things and where the factors of 2 go. The one factor that's here that's a little disturbing that you should notice is this factor of I. So normally in Lorentzian signature, we would take this ADM momentum to be real, which means that the stress tensor is imaginary. Before I explain that, I should also comment you could do the exact same thing for all of the other sources here to switch between operators in the theory and momentum variables. The reason this sort of dictionary is possible is because we've sort of got 2 different notions of conjugate variable in physics. We've got a symplectic structure between sources and operators in field theory. And we also have a classical mechanics or quantum mechanics symplectic structure between position and momentum. And what really is making this holography tick is that we're conflating these 2 symplectic structures. So we're identifying the one with the other, even though a priori they look different. Now, the fact that the stress tensor is imaginary when our Cauchy slice is embedded in Lorentzian signature, that should be disturbing at first. It turns out it's a necessary feature of any Cauchy slice holography theory. Fundamentally, I'll show you the geometry of this in a minute. It's because the T-squared field theory exhibits what I call spontaneous CPT breaking. So that's a very exotic phenomenon because usually unitarity and Lorentz invariance prevents you from breaking CPT symmetry even spontaneously. In this case, you can, and the reason you can is not because we're breaking the analog of Lorentz invariance, which is just Euclidean notations. It's because the CPT theorem also relies on this being the partition function of a unitary theory or a Euclidean signature, a reflection positive theory, and the Cauchy slice theory is also not unitary in this sense. It's just a fact that Wheeler-DeWitt states in quantum gravity do not satisfy reflection positivity. So if we're going to do this at all, we need the partition function of a non-unitary theory, or at least a theory that would be non-unitary if continued to Lorentzian signature. All right, so what we're going to do is we're going to start now with a Euclidean holographic CFT that's defined on some metric GAB. So this could be whatever your favorite ADS CFT duality is. So we could say, for example, n equals 4 super Yang-Mills in Euclidean signature. We're going to need to pick out a conformal frame for this metric because we're about to turn on an irrelevant T-squared coupling that is going to, in any case, break conformal symmetry. So even if we were in odd dimensions where there's no conformal anomaly, we would still need to pick a particular conformal factor of the metric before beginning this process. At that point, we turn on an irrelevant coupling whose coupling constant is mu. Now, we're actually going to take mu to be a global variable here. So it's the same everywhere on the Cauchy slice. There's actually an alternative picture where you let mu be spatially dependent so that you do a different amount of deformation in different places. But everything you can do by doing that, you could also have done by just changing the original metric you start with and then doing a constant mu. So we found it technically easier to just have the constant mu. But there's people who did something a bit similar to what we're doing with the other convention, Caputa, Kruthoff, and Periker. Although they didn't they didn't evolve all the way into Lorentzian signature. They're trying to construct a theory on the t equals 0 slice. Okay, now let me show you the geometry of how this works. So one nice example is if we pick GAB to be a uniform hyperbolic geometry. So like if you imagine you put n equals 4 super Yang mills on a sphere, I take half of that sphere, I can put that's conformal to a hyperbolic metric. So I start with the Euclidean CFT on this hyperbolic metric. I turn on the irrelevant coupling. What's going to happen is that as mu gets bigger, the boundary on which this theory is defined, where there's Dirichlet boundary conditions for the metric, is going to move towards the t equals 0 slice, the slice of symmetry, as we move in the imaginary time direction. At a certain finite value of mu, it actually reaches this slice. And if we make mu bigger than that, we actually end up in Lorentzian signature with a slice that bulges either to the future or to the past. Since if we have multiple, these correspond to different quantum mechanical saddles, different quantum gravity saddles, so we should really sum over both of them, which means that our partition function is going to end up being a sum of two terms, each of which separately breaks time reversal invariance. That's why I call this spontaneous time reversal breaking. Now we haven't touched P or C in this setup, so that's why we also break CPT. Okay, now to verify for yourself that this is what these slices actually do, you could do this more generally than this symmetrical case, but in this very symmetrical case, everything about where this slice is embedded is determined by the Hamiltonian constraint equation. So the scalar part of the Hamiltonian constraint equation just says that this like trace of the extrinsic curvature squared, or trace of the stress tensor squared, is controlled by the Ricci scalar minus twice the cosmological constant. This is the bulk cosmological constant. So there's a certain critical value of R, which is measured relative to this constant mu. So there's a certain critical value at which the sign of pi switches from being real to being imaginary. Sorry, which switches from being imaginary to being real. So it happens when we're on a slice that has R less than 2 lambda if we fix mu to be unit. Okay, so this CPT breaking might seem a little bit disturbing, but here's an analogy that might make you feel better about it. The same thing happens. There's a question. I can't hear you.
Right, I will unmute. Right, sorry. Thanks for, yes. Go ahead, Nikolai.
Hi. Before you move on to this analogy, I wanted to ask, so the perspective that you explained is somehow a holographic one. Can you, do you have a good idea what happens in the quantum field theory? Like if I do this to n equals 4 Yang mills, what's going to happen to n equals 4?
Yeah, so I mean, you can work out a number of, you can work out endpoint functions, for example, and it's well-defined, at least in the limit that n goes to infinity. So I'll say a little bit more about this in the talk, but you could calculate endpoint functions of the stress energy tensor, for example, and you'll find that the 1-point function turns into something that looks like the Hamiltonian constraint, and the 2-point function turns into something that looks like the bulk 2-point function of the extrinsic curvature when you have this Dirichlet boundary condition.
Right. My confusion comes from the fact that you're doing an irrelevant deformation of n equals 4, and then all bets are off, right? You will generate all kinds of operators.
Normally that's what happens, but the t-squared deformation is actually special. It's better behaved than a typical irrelevant deformation.
Right, but this is
in
only
higher
two
than
dimensions.
right
This is
in
not
higher
doing
than
more
2 dimensions. It potentially has field theory problems, but they go away at n equals infinity because the n equals infinity lets you factorize the expectation value of the t squared into two expectation values, one on each stress tensor. So it works in the n equals infinity limit. We said some words in our paper about what to do in 1 over n corrections. As I might have time to mention at the end of the talk, there are some open questions about how you would UV complete this at finite n. All right. So to proceed, so suppose you're doing cosmology, and to make things simple, we'll do what's called mini superspace cosmology, where you the only variable you consider is the scale factor of a maximally symmetric universe. So let's say we're doing de Sitter, and we just have spheres with some scale factor A. And we're going to take the cosmological constant to be positive in this example, so that the classical solutions would be de Sitter. Now, there's a Hartle-Hawking wave function, a no-boundary wave function, and that no-boundary wave function looks like this. There's a transition that occurs at a particular value of A that corresponds to the what you would have at the t equals 0 slice. So the sort of critical sphere, the de Sitter radius. So when you're smaller than, when your scale factor is smaller than that critical radius, your no boundary saddle is Euclidean, and you get an exponential-ish looking thing for the wave function. If, however, you're on the other side of this critical boundary, your saddles become complex. The easiest contour to think about is if you do the Euclidean path integral up to the t equals 0 slice and then evolve from there either to the future or the past. You have two choices because of time reversal invariance. The Lorentzian piece gives you phases, and so what you end up when you add both saddles together, you get a wave function that's still real, but it's oscillatory. So this sort of oscillatory wave function is what we would call spontaneous time reversal breaking, because it's a sum of two complex exponentials associated with an expanding universe and a contracting universe that are time reversal. They're not time reversal and vary individually, where these sectors are sort of clearly distinct from each other. So right at the critical radius, something particularly weird happens. The WKB approximation actually breaks down. So if you tried to do linearized graviton fluctuations on the background with this boundary condition, it doesn't actually work because you have infinitely many zero modes. The same thing would actually happen in this mini superspace model, where it means the WKB approximation breaks down. But interestingly, even though the WKB approximation to this thing that looks like the same thing happens to the Airy function. The WKB approximation breaks down at the critical spot, but the actual wave function you're approximating makes perfect sense, even at this transition. So hopefully the same thing is true, even in the situation with infinitely many degrees of freedom. Okay. So now let me tell you what you actually do to get this deformation. Our work was strongly inspired by the paper by Hartman, Kruithof, Segelin, and Tagini. So let me start with, so here's this deformation, and let me explain it piece by piece. We start with a CFT that is the original holographic CFT. It's a function of various variables. Okay, if we're in odd dimensions and there's no conformal anomaly, then the statement of the conformal invariance would just be that pi equals 0. If you're in even dimensions, there's an anomaly term which we'd have to include as well. Let's assume for the moment we're in odd dimensions. Now, what you do is you deform by doing a path-ordered exponential of some deformation operator. This epsilon here is only to cover the case where there's long divergences due to an anomaly. So for the moment, let's just pretend that epsilon is 0. So what you do is you integrate this deformation from 0 to whatever your value of mu is. And that path-ordered exponential gives you a new partition function. Then at the outside, we also have to conjugate it by some counter terms that actually aren't physically significant. They're just to do a field redefinition that makes things look like the general relativity Hamiltonian constraint. So this whole structure here defines this partition function. And basically, the key point is that O lambda and the counter term are chosen to be whatever they need to be, so that when we start with if I insert pi here into the equation acting on z, I get 0. So what happens is if I commute pi past all of this stuff up to terms that look like the spatial momentum constraint, which always vanishes for any covariant partition function, this pi is supposed to turn into the Hamiltonian constraint when I insert it here. So what I end up with is a partition function that's the property that if I act with it with the ADM Hamiltonian constraint equation, I get 0, which means it's a Wheeler-DeWitt wave function. Now, in even dimensions, when there's a conformal anomaly, you have to be a little bit careful because there's some extra stuff in here, and you got to regulate things a little bit here with this epsilon, but you end up in the same place. So O lambda here, because it's like a deformation of your Lagrangian, it takes the form of a spatial integral of some Lagrangian term x. All the terms in the Lagrangian are organized with powers of lambda, where the powers are chosen so that lambda, which is basically the same variable as mu, but inside this integral, is chosen so that lambda is the only dimensional parameter in the flow. This vastly simplifies the algebra. I don't have time to really go into why, but let's say it makes the difference between there being the commutators closing after a single step versus infinitely many commutators and infinitely many terms. So you definitely want to use this convention. Okay, so as an example, the deformation found by Hartman et al. That works for to get 3 + 1 general relativity. If you start with a 3-dimensional holographic theory that is hypothetically dual to pure gravity at low energies, you would turn on a deformation that's quadratic in the stress energy tensor, but it's also got some terms in the quadratic expression that involve the Einstein tensor GAB and its trace. And then there's the powers of lambda are chosen to be dimensionally correct, and there's a coupling constant in here which is related to you have to choose it to match to the Bulk-Newton constant. Okay, I put in normal ordering here. There's a story about how you would do 1/n corrections in our paper, but if you like, you could just think classically at the moment in the sense of n equals infinity. Okay, so one of the things we did in the paper with Gonzalo and Rifat is to show that this could be extended to the case of an arbitrary Hamiltonian constraint, which is good because typical examples of holography have a bunch of low energy fields, so it's not just gravity. So what you do is you can start with any bulk Hamiltonian constraint you like. There'll be some consistency conditions with the CFT in a moment, but for the moment, take any Hamiltonian constraint you like that satisfies the closure relation. So that's just the commutator of two Hamiltonian densities with itself gets you this term that involves a derivative and the spatial diff constraint, which vanishes. It basically expresses the conservation of the stress tensor. So closure is something we usually demand in GR, in the Hamiltonian formulation. And we're assuming that it closes with the usual ADM algebra. Okay, so now what you do, starting with this Hamiltonian constraint, there's a procedure for acting with a counter term. So you have to look at all the terms of the Hamiltonian constraint, and if you reinterpret them as CFT variables, some of them will look like relevant things, some will look like marginal things, and some will look like irrelevant things. You've got to conjugate it by a counter term to get rid of everything that looks like a relevant thing. It's just like a field redefinition. And then for the marginal terms, there's an anomaly matching constraint where it's important that all the marginal terms in the Hamiltonian constraint have to match with anything that, with the log divergences of the CFT by this equation, which involves the Weyl generator and the anomaly. This anomaly matching condition gets you the usual anomaly matching conditions involving central charges C and A. It also gives you the usual conditions relating mass squareds of fields of the bulk, 2 dimensions of operators on the boundary, that sort of thing. Then you can just immediately write what deformation you need to plug into your deformation in terms of the generator and Weyl transformations and this counter term modified Hamiltonian constraint. Okay, so there's some procedure that you can turn the crank and do this for any Hamiltonian. Presumably, if you try doing it with a Hamiltonian that doesn't in all respects match the bulk physics of the boundary CFT, something will go wrong. But in odd dimensions where you don't get the central charge constraint, it's maybe not immediately obvious what does go wrong. So that's a little bit of an open question here, but I'm pretty sure something must go wrong. Anyway, so it'll probably be important that you pick whatever Hamiltonian constraint is the actual Hamiltonian of the bulk theory that's dual to your CFT. So now having done that, something remarkable pops out, which is that you actually get an implementation of the ADS CFT dictionary that relates you between CFT states and bulk geometrodynamic states. So it's basically maps between bulk states and boundary states, where the bulk states are defined on Cauchy slices, and if you know the T-squared partition function explicitly, you basically know these maps explicitly as well. So first, I want to talk about the map from the bulk to the boundary. So there's a very natural way to do this. It relies on the fact that if I have a partition function, so if I have a partition function on a closed manifold, I just get a number. But if I have a partition function on an open manifold, I have to specify boundary conditions on that open manifold, and that's equivalent to specifying a state of the theory on that boundary. So in the case where I have this asymptotically ADS setup, there's a boundary out at infinity. I need to specify some state of the t-squared deformed theory out at infinity. But when I go out to infinity, the scale factor of the metric on the Cauchy slice also goes to infinity, which is like zooming out. So as I go to the boundary, this t-squared deformed theory actually, the irrelevant term becomes increasingly unimportant. And so out on the boundary, its state should just be the same as the states of the original CFT that I started with. So what that tells me is that my partition function of this theory on this slice, actually, I didn't quite specify it sufficiently in this equation because it's actually not just a function of the spatial metric and of the other configuration space variables / sources. It's also a function of some CFT state that I've written in some arbitrary basis chi. This could be energy eigenstates, for example, on this boundary. So my partition function depends on both of these things. Now what I can do is I can define a map for the bulk to the boundary this way by saying I'll pick whatever initial configuration space data I like in the interior of this Cauchy slice. Now my partition function is functionally depending still on this boundary condition, and that's the same as a CFT wave function in whatever basis I've picked. So for example, if chi were an energy eigenbasis, then this would give you the CFT wave function in the energy basis. But it could be anything you like. Okay, so that map is a pretty straightforward one. You just specify initial data, you get a boundary CFT state. But the initial data could be quite weird. For example, you could have a black hole, you could have some bag of gold configuration where you have a whole cosmology behind the throne of the black hole. This map doesn't care. You can still do it. Okay. The other direction, we also want a boundary to bulk map. So there we have to do something a little bit different. There we need to sum over the chi variables now to get a Wheeler-DeWitt state with now it's going to have amplitudes for all possible times in the Wheeler-DeWitt patch. So what's going on is the CFT boundary state can't actually be dual to just one Cauchy slice because the gauge symmetries on the boundary aren't the same as the gauge symmetries on the bulk. It's only the physical information on both sides that's isomorphic in the ADS CFT dictionary after you mod out by the gauge symmetry. So what this means is that a CFT state, when we map it back into the bulk, has to give us an entire constraint equation satisfying Wheeler-DeWitt wave function that's effectively a quantum superposition of all possible times, including wiggly slices. So you get that Wheeler-DeWitt state by, again, you start with the same partition function, but now we multiply it by the CFT wave function, which is the part that we're going to pick. And now we're just going to integrate over the chi variables, which is equivalent to the inner product, imposing the inner product on the boundary side of this dictionary. I've written this as an integral here, but depending on whether chi is a discrete or continuous basis, it could end up being a sum or an integral depending on your convention there. So the end result, you have something that now just depends on g and phi, so it's a wave function of these spatial variables. And that wave function, by the argument we just went through, satisfies the constraint equation. So it includes all possible kinds of the bulk that glue onto this boundary. Okay, so since we've got a bulk to boundary map, And since we have a boundary to bulk map, you might think these are going to be inverses, right? Well, they're not inverses. They're not quite inverses because of this way that you get time evolution when you map from the boundary to the bulk. The correct statement is that if I compose these two maps together to get a bulk-to-bulk map, it looks like the bulk gravitational path integral. So we hypothesize in our paper and show some evidence that in a suitably semi-classical context, the composition of these two maps is the same as the gravitational path integral. So the way that works is I start with initial conditions defined on some with some ket states, so some initial data on some Cauchy slice, and then I want to define a dynamical inner product with some final conditions where I do it by summing over possible manifolds that go between the initial metric and the final metric. I should put the phi's here too, really, of a path integral over the g and the phi mod diff symmetry of e to the I times the gravitational action. Now, one note, even though I've called this an initial and final state, in order for this to satisfy the constraint equations, it's actually necessary to allow for all possible time relations between the two slices. So the bra here could be either to the future or to the past, or partly to the future and partly to the past of my initial slice. Now, so this is the natural, naturally follows if you believe the statement of our dictionary, which is basically, since things work, since you get the right Hamiltonian constraint formalism, it seems natural to propose you also get matching partition functions at the path integral level. This is what this would say. Okay. All of this is modulo the usual questions that people argue about all the time about what your choice of contour for the gravitational path integral should be. We don't actually resolve these questions in our paper, but it's possible you could learn something about them. Okay. So now there's, in this time evolution, we're holding the boundary fixed, but there's something else you could do, which is you can also choose to evolve for a finite time on the boundary. Where evolving for a finite time on the boundary CFT should be like a global symmetry from the perspective of the ADS quantum gravity. So you can do this. You can take a partition function that evolves for a finite amount of time. The way you do it is you just take this t-squared deformed Cauchy slice path integral. You take two of them and put them at the top and bottom of a cylinder to be the initial and final states. And then at the sides of the cylinder, you put the usual undeformed CFT partition function. It's actually technically convenient often to slightly infinitesimally deform it just to make these junction conditions a little easier to work with, but morally what we're doing is this. So then if what we're proposing is correct, this is now like a closed partition function, so it's a number, and that number should equal the same as the bulk quantum gravity path integral that would take you from one Cauchy slice to another Cauchy slice, where now they're anchored at different boundary times. Okay, so one thing we were able to show is that the two theories have matching Hamiltonians, so that's pretty good evidence that they have the same time evolution. So what we did is we looked at the Cauchy slice that goes to the boundary CFT. We wanted to turn to the CFT, but we regulated it slightly just with an infinitesimal t-squared regulator, just so both of these were the same theory. So now these meet at some angle. And it turns out there's a non-trivial junction condition associated with this sharp angle where the stress tensor instantaneously jumps in a manner that depends on the extrinsic curvature. And when you work it out, at least classically at n equals infinity, where you don't worry about operator orderings, you end up with an equation that looks like the CFT Hamiltonian equals the ADM Hamiltonian of this Cauchy slice theory. All right, another thing you could do that isn't really in this paper, but is going to come out in a later paper, is you could discuss what is the state counting the state counting entropy of a codimension 2 surface of the bulk. And this is just from the perspective of the Cauchy slice theory, this is just like a microcanonical entropy, where you're just maximizing the number of states that can fit through a cylinder of a particular size and a particular energy. So when you do this, you find an interesting result. Roughly speaking, you find that the microcanonical entropy, first of all, of a codimension 2 slice, first of all, it only depends on the intrinsic codimension 2 data. It doesn't matter which codimension 1 slice passes through it. Second of all, if you have a marginally trapped surface, your microcanonical entropy equals A over 4, the Bekenstein-Hawking entropy. But if you don't have a marginally trapped surface, it could be bigger or smaller. In particular, for trapped surfaces, you find that it's actually bigger than A over 4. And this is associated with the fact that this is a non-unitary theory that has imaginary energy eigenstates. So it's actually needed for consistency to include these imaginary energy eigenstates to go into Lorentzian signature. And this is why, if I have an Einstein-Rosen bridge and a Cauchy slice that goes very close to singularity with very small area, I still have enough states to map me between the left or the right CFTs. On the other hand, for an untrapped surface, where the extrinsic curvature is space-like instead of time-like, I get the opposite. I get less than A over 4 allowed states. For a stationary black hole, the S is actually the same for every cut of the space-time that separates the left and right CFTs. So that's compatible with this. All right, I'm nearly done with what I wanted to say, but let me just go in a somewhat more speculative direction. So as I mentioned earlier, the t-squared deformation is solvable without the usual issues that afflict irrelevant deformations in 2 conditions. One is when d equals 2, which is the case of pure general relativity. And the other case in d greater than 2, or if there's matter in the Hamiltonian constraint, this requires n equals infinity to be well-defined, or probably you can make things work in a 1 over n expansion if you regulate things in the way we describe in the paper. Away from these cases, it's not actually clear that the t-squared deformation is fully well-defined. For all the usual field theory reasons, the irrelevant couplings are problematic. So what we'd really want to do from an RG flow perspective, we'd really want to find some UV completion of this theory. So suppose we found that. It's like the difference between a bottom-up approach and a top-down approach. There's an RG flow of this. This theory has a non-trivial RG flow. It's somewhat surprisingly, because this reverses the usual direction of IR versus UV, we usually think about an ADS CFT. Somewhat surprisingly, the usual boundary holographic CFT is actually the IR fixed point of this theory. So then you do an irrelevant deformation, and that's the t-squared deformation, to just push yourself up a little bit up this RG flow. But what we'd really like to do is to define a model that's UV complete on the boundary and then just flow down. If we flow down, then maybe in some generic sense, modulo, like the usual fine-tuning problem of the cos modulo constant and so on, maybe in some generic sense, we could flow to some class of models would flow to something that looks like general relativity. Now, what we claim in the discussion of our paper is if such a UV completion were found, you could then just interpret it as a UV completion of this gravitational path integral, and it would actually define a non-determinative bulk quantum gravity theory, which is also known as the Holy Grail. Now, we don't claim to have done this, but you could argue that it might actually be easier than the traditional problem of making quantum gravity make sense of the bulk. So the traditional non-normalizability problem of quantum gravity also involves irrelevant deformations, but on the boundary side, we have some things helping us. One is that the theory is actually defined on a fixed background metric. Yes, you can vary it, but you can also hold it fixed and just treat it like a field theory. So field theories that don't involve dynamical gravity are usually easier to UV complete. We wanted a Euclidean signature because Cauchy slices are Euclidean. That again makes regulators easier to impose. And a lot of regulators are not unitary, but we already sacrificed unitarity, so maybe that's not an issue either. Of course, at the end of the day, there has to be some reason why bulk observers will only see positive probabilities. We're sort of pushing that problem out to a future day, but roughly speaking, what we expect to be the answer to this is that what looks like is true is that your bulk theory will have a positive inner product as long as you consider only a restricted class of regions. So you have to view bulk quantum gravity only with particular boundary conditions. One boundary condition that seems to be nice is asymptotically ADS, which is why ADS CFT is dual to unitary CFTs. But another thing that's nice is when the boundary is not a trapped surface where the extrinsic curvature is imposed to be space-like or null, then it seems like that's naturally associated with not needing to have these imaginary states on the boundary. So there's definitely some philosophical and conceptual points to resolve there, but that's the direction I'd like to see things go. I was a little confused at first how it could be that a boundary theory could be non-unitary when the bulk theory is unitary, but it turns out in another recent paper of mine, I argued that the bulk gravitational path integral also has pathological negative norm states in it when you quantize it with a fixed boundary, a fixed codimension 2 boundary surface, and it's trapped. So these things in the context of ADS, you don't have negative norm states if you consider a Cauchy slice as the entire ADS, but if you want to consider a Cauchy slice, a partial Cauchy slice that stops at some point in the bulk, then you might be in trouble. Okay, so I'm out of things to